This meeting is being recorded.
Okay, so welcome everyone to the second episode of the 8th season of the Isogeny Club. Today we have Julien Soumier giving us a talk. He's a PhD student at the Université de Lorraine. Okay, that's how I say it, sorry. French pronunciation might have been a bit off.
It's okay.
And he will talk to us about the different modular representations for higher dimensional supersingular isogenies. And yeah, please, the floor is yours, Julien.
Okay, so thank you very much. So thank you very much, all of you, for being here today. And of course, many thanks to you, Maria and Jonathan, for inviting me here and giving me the opportunity to talk a little bit about the module representation. So what I'm going to present comes from a joint work with Aurel and Damien Robert. Maybe before going a little bit into the details, I just wanted to make a slide to try to motivate you to work with the module representation and what the purpose, in fact, to look at such a new tool. So the fact is, in isogeny-based cryptography, we are very interested in a powerful tool to compute isogenies, such that the Deuring correspondence or the ideal class group action along with all the Clapoti algorithm family. Taking the example of the Deuring correspondence, it's really some tool that we can use to compute isogenies between elliptic curves, so something that must be hard in practice, but we can do that because we have some extra information, in this case given by the endomorphism ring of the curve involved. And the fact is those two tools are in fact very useful, but are restricted to the one-dimensional case. So a very natural question that arises is there any similar framework to that could apply to more general abelian varieties? Fortunately, the answer is yes, and it's provided by precisely the Deuring correspondence. That is, in fact, a rather new way that we have to represent polarized abelian variety, and of course to compute their morphism, assuming that you have some extra information given by this module representation. Moreover than being just something that generalizes existing tools, the module representation is in fact kind of cryptographically friendly. So there is several arguments to state something like this, but I will focus on two. So first, in fact, we are working with some lighter objects than when we do the correspondence, the Deuring correspondence, for example, and I'm going to be a little bit more precise later. So it led us with Damien and Aurel to improve the complexity output, for example, of the Clapoti algorithm when we are working with modules. And maybe another argument that is developed in a Damien paper from 2024 about modules is that we expect that in the generic settings of the module correspondence, the attacks, quantum attacks such as given by the Kuiperberg algorithm does not apply. So there is several reasons for that, and I won't go into the detail, but something we can notice is that we're not acting by a group on the set of abelian varieties, but by something a little bit more abstract. So, okay, I hope that now it's you're at least a bit motivated to look in more details at the module correspondence. And just before introducing you those objects, I'm going to tease you a little bit about the result I'm going to present in this talk. The first main result I want to present is our solution of the principal ideal problem. So to state it properly, I need some just notation. So in the following of this talk, this letter O will denote a maximal quaternionic order in the usual quaternion algebra ramified at P and affinity. So it really behaves like the endomorphism ring of a supersingular elliptic curve. So what we did with Aurel and Damien is that we provide an algorithm that on input an ideal in this type of matrix swing, we can in fact output a single generator of the same ideal. So together with this, the presentation of such an algorithm, we also provided proof of concept implementation of our algorithm in the software SageMath. So it's really an algorithm that input takes a finite set of generators of an ideal and output a single one, okay, which will be different from each one of the first. Another result that I want to present to you today is something that we can call as a generalization of the existing Clapoti algorithm in one dimension. So I won't go into the detail on this slide, but you can really see it as a tool that relies on the fact that we can compute double pass like this between polarized abelian varieties. Double pass meaning that we can compute two isogenies of different degree, so that they don't speak to each other. And before moving to abelian varieties and their modules, I just wanted to highlight some consequences. So the first is that those tools allows us to, given the module representation, switch between other already known and used representation, such as, for example, theta coordinates or endomorphism ring representation. I'm going to be a little bit more precise at the end of this talk for switching between representations. Another result that I wanted to highlight today is the fact that thanks to the module representation, we are now able to compute isomorphisms between any kind of maximal abelian varieties of same dimension. So it will be at some point in this talk, the very technical slide, I'm going to explain how we managed to do something like this. Okay, so let's move on and let me present to you the main objects that we are going to use in this talk. So now I'm going to be a little bit quick on abelian varieties, but I will focus and give a lot of examples concerning the Hermitian modules. So just a quick recall about abelian varieties. For us, an abelian variety will be a projective variety defined by the zero locus of polynomials that comes naturally together with an abelian group law. And of course, those two properties have to match well in some sense. If we look at dimension 1 abelian variety, we actually recover exactly the elliptic curves that can be defined by equation like this, and that were already used not only in post-quantum cryptography, but also in classical cryptography. For example, when you're trying to connect to a secure website, your computer is dealing with elliptic curves. And now, if you want to go in higher dimension, you can look at product of elliptic curves, but something more, maybe something fancier happens that you can encounter Jacobian of G curves and other things. Up to my knowledge, today, those type of abelian variety are mostly used in post-quantum cryptography. So just now, I'm going to give some definition, not for you to remember it precisely, but more to emphasize the fact that I'm going to work with a very specific family of abelian variety. Precisely, I'm going to work with what we call maximal abelian varieties. So from now on, I'm just going to work over a finite field of p-squared element where p is a fixed characteristic. So a maximal abelian variety is really an abelian variety that has the maximal amount of points on it. Okay, it really reaches the upper veil bound that is prescribed. So some example of such maximal abelian varieties. The first, maybe the easiest that we have already in the cryptographic setup, is when we work at the characteristic that is 3 mod 4. Then we have those base curves that is in fact maximal. Now, if we also made the product of maximal elliptic curve, we end up with a new maximal abelian variety. And I just wanted to notice that we really are in the quaternionic case since maximal elliptic curves are supersingular. So you see that it's very some precise family of abelian variety, but it's in fact the one that we encounter when we are doing isogeny-based cryptography. So I'm pretty fine staying in this context. So now we can. I'm going to stay to say a very strong result about maximal abelian varieties, and to do so, I'm just fixing some maximal elliptic curve E, whose endomorphism ring will be still denoted O. Okay, so this one is fixed from now. And something very surprising that happened when we are working with maximal abelian varieties is the fact that for each dimension, there is only one isomorphism class of such abelian varieties. This means that if you give me any maximal abelian variety of dimension at least 2, say G, say J, then there will always exist an isomorphisms between the variety you gave me and the product of G times the fixed curve E, which is maximal by what I said just earlier. And so a natural question arises, how can we compute such an isomorphism phi? So last year with my supervisor, Pierre-Jean Spenlauer and Pierrick Gaudry, we tried to give a first answer to this problem where we solved the case where A was given as a product of elliptic curves. And since we need to compute an isomorphisms, we need to assume that we have some extra information, which in our case was the endomorphism ring of the curve involved. More recently, Montesinos showed that, in fact, when we are reducing to the case of surfaces, of abelian surfaces, we can, in fact, solve the generic case, assuming that we know what we call the AQO matrix of the abelian variety given. And what I'm going to show today is that thanks to the module representation of the abelian variety A, we can in fact solve the very general case. So for me, it was maybe from a personal point of view, what made me start to look at Hermitian modules since soon after that we released our paper with Pierre-Jean and Pierrick. Damien wrote me an email and saying, if you look at the module representation, then with some algorithm and the help of Aurel, we could manage to draw a very general algorithm. And so he was right. And now I'm going to present specifically what helped us to solve the generic case. So I'm going to introduce the module correspondence that I was talking about for so long. So first, I need to define what are the Hermitian modules. From an abstract point of view, M, a module, will be a finitely presented torsion-free module of rank J over the ring O. So you can forget about this, and since in the following of this talk, I'm just going to speak about good module to shorten the words. And if you don't know what such a module is, don't worry, you can really think of M as space generated by some column vectors inside O to the G. Okay, so there is really a lot of similarity with what happens when we are dealing with classical linear algebra over a field. We are really working with vector over a special ring, which is O. But so this will be the object as we are interested in, but we are going to add some extra information on them, which will be given by what we call an Hermitian form. So an Hermitian form is a biadditive map on M that takes on input 2 elements and that output an element of the base ring O. So we assume some specific condition, here you see the overline is just the usual conjugation in the ring O. So if you see our good module as spaces generated by vectors, you can really think of the Hermitian form as a little bit weird scalar product on this space. We have and we assume also that the form that we have leads to a quadratic form that I denote QM, which is definitely positive. But this is more technicalities. So from now on, when I say that something is an Hermitian module, it will stand for such a couple where I have on one hand a good module of rank G, say, and in the other hand I have an Hermitian form on it, which is really a pairing on it. So this is a rather abstract point of view, and I want to give some example to grasp a little bit more what is going on behind this definition. So maybe the easiest example I can give of good module of rank G is the ring O itself. So it's a rank 1 module over O. And the natural animation form to consider is the one where you multiply on the left by x and you multiply on the right by the conjugate of y. Maybe a more interesting example is given by ideal of O. So instead of looking at the module given by O, we look at the module of rank 1 given by an ideal of O, staying with the same Hermitian form, and one can check that it's once again give us an Hermitian module. Now we want to go in higher dimension, meaning in higher rank module. We can make the direct sum of Hermitian module, and it stays an Hermitian module. In particular, something that will be very important for us is the base module of rank G, which is just G copies of the ring O, so really the vectors over with G coordinates over O. And the Hermitian form that we put on it is just the same Hermitian form as H0, but acting component-wise. So it's really something that we can grasp. Okay, and something very interesting about the theory of Hermitian module is that there comes with their own duality theory. So I won't go into the detail for this talk, but we can define the dual theory of such a module as we do for abelian varieties. And we are going to say that an Hermitian module is unimodular when the HM, the Hermitian form, gives us a bridge between the module M and its dual, which is in fact an isomorphism. So this is really some duality property. We want that a module which is unimodular had very good properties regarding its dual. The easiest example that I can give is the fact that when we look at the example of an ideal of O, and if we stay with the same Hermitian form H0, this is not unimodular. However, if we divide H0 by the reduced norm of the ideal A, we end up with a unimodular Hermitian module. So here I want just to take a few seconds to notice that we can really think about this as the reflection that happens for abelian varieties. When we are considering abelian varieties, we can look at the polarization, which are isogenies between an abelian variety and its dual. And we say that polarized abelian variety is principal, a polarization on abelian variety is principal when it induces an isomorphism between A and its dual. Also, in the one-dimensional case, when we look at the polarization on an elliptic curve, in fact, we can show that it will always be a multiple of a canonical one, which will be principal. It's really the same thing that's happening here. And in fact, we can give a precise statement of what I just tried to explain with my hands, which this correspondence comes, in fact, from precisely the module correspondence. So I'm going to talk about a correspondence, but here, for those who knows, it's something that beneath it is really an anti-equivalence of category. So it's really a strong correspondence. I'm going to maybe more precise later. So the fact is, if I have a maximal abelian variety A, I can look at the morphisms between A and the fixed curve E. Here, the morphism are the morphism of varieties that are also morphism for the group. And this homomorphism set give me, in fact, a good homodule, so a good module M over the ring. In the other direction, there exists something that is called the module action, which is a little bit more hard to understand, and that I won't going to describe today. But when I have some good homodule of rank G, if I apply this module on the fixed elliptic curve E, I end up with a maximal abelian variety of dimension G. Okay, so this is really a strong correspondence, as I say. In particular, it will preserve the rank of the object you are working with. So if I work with the rank G module on the module side, I will in fact work with the dimension G maximal abelian variety. And as I said before, this equivalence of category preserves the duality properties we have on both sides. So to the dual of the module M corresponds the dual abelian variety on the geometric side. Okay, so now that we have some overview of the module theory, I'm going to move on to our solution to the principal ideal problem. But before, once again, I want to give some example. For example, we can ask what is the Hermitian module associated with the abelian variety, the canonic abelian variety, maximal abelian variety in dimension G. And it's precisely the base module of rank G. Okay, so it really corresponds the base curve to the base module, Something more interesting is when we look at the action of ideal over the elliptic curve E, then we in fact recover the Deuring correspondence. Now, if we look at higher dimension things, once again, when we consider the direct sum of ideals, for example, we recover the product of the corresponding elliptic curves. So it's really coherent with the external sum. So just a few seconds later, I just said that we recover the Deuring correspondence when looking at the action of ideal. But in fact, we do a little bit more than that, and it has to be related to what I said in the beginning of this talk, because when we look at rank 1 module, we in fact look at ideal that are embedded in the ring O. So what I mean is that if we look only at rank 1 module, we in fact look at objects which carries less information at each step of the computational process. What I mean is that I don't need to remember the inclusion that I have between my rank 1 module and the ring O. And so that it might be an explanation why using this module representation, we manage with Aurel and Damien to lower the output of the Clapoti algorithm, for example. We expect that this type of object will be more flexible. Okay, so let me go on to our solution, to the principal ideal problem. But first, I want to explain how does this problem relate to Hermitian module. So maybe I can start by translating the Deligne-August-Shioda theorem in terms of modules. So really, it's the same thing. I suppose that you give me a good module of rank G being at least 2. Then there will always exist an isomorphism between M and the base module O to the G. Here, before moving on, just a quick remark, because this means that if you give me an Hermitian module, so a module together with this weird scalar product, then it will be isomorphic to another Hermitian module where the module M will be precisely O to the G. We can in fact just pull back the Hermitian form that we have on M. And so if we now look at this for G equal 2 and looking at the gram matrix of the Hermitian form induced on O to the G, we precisely recover the matrices that appear in the Clapoti paper. You know these matrices that are Hermitian and that have determinant 1. Looking at the gram matrices of such a representation gives us the same matrices. And in fact, for our new solution to the Clapoti problem, we could use a lot of the tools that the author developed in their papers. So, okay, now going back to the problem of the principal ideal problem, the fact that we can notice is that finding such an isomorphism among, in fact, to find a basis of my module M. We just need to find the preimage of each one of the canonical vector of O to the G. Okay, but something more interesting maybe is that computing a basis of M amounts to principalized ideals in this matrix ring. Okay, so it's G by G matrices over the ring O. So this can be seen as a baby case of the Morita equivalence, but here I'm going to be a little bit more precise and present a little bit more down-to-earth approach. So what we know by linear algebra is that when we look at the module over O, which is generated by some column vectors like this in O to the G, so with G coordinates, we end up with the same elements that we have in the module generated by the columns that appear in the right ideal generated by those matrices. So you can see here, sorry, where we just glue together the columns that we have. Okay, so this is really something known, that working on one side is the same thing as working on the other side. But that means that if we manage to principalize the ideas we're working with, so if we manage to find a single matrix which have only G columns that generate the same ideal, it means on the module side that we manage to find G generators of my module M. But since we are working with a rank G module, it means that we have in fact compute a basis of our module M. So this is how those two problems relate. And this is why now I'm going to mainly focus on the principal ideal problem, and I'm going to give the solution that we provide with Damien and Aurel. Okay, so this is what we're going to do. Sorry, I'm going to drink a little bit. Okay, so let's move on. So now I suppose that you're giving me several generators, a finite set of generators of I, and I want to output a single generator of I that I denote alpha here. The general strategy we have with Aurel and Damien is that we're gonna apply the local global principle, meaning that in fact we will only find the generators that will principalize our ideal locally at every prime Q. So for those that are not familiar with the local global principle, you can really think of it as a tool we have to break down the initial hard problem we have over the ring O into easier problems over easier rings. So the fact what we won is that we had at first a hard problem, and now we have to solve easier problem. But what we lost is that now we have to solve infinitely many problems, one for each prime. To address this issue, we're going to proceed in two steps. But first, I'm going to fix a small prime denoted L. And so now I want to solve this problem of finding global generators at each localization for each prime Q. So the first step that we have is that we're going to principalize our ideal everywhere simultaneously, except precisely at L. Because in fact, we can show that it amounts to work in this matrix space where you assume that you can invert the prime L. So this is really the first case where we do an infinitely many steps in one time. And then in the second step, we need to localize the remaining ideal exactly at the prime L. And so this will, to deal with this problem, we're going to work in a matrix ring over L-adix integrals. Maybe a little bit more detail. So for the first step, we're going to, in fact, compute an element alpha 1 here that will principalize our ideal, assuming that we can invert L. So the tool that we used to solve this problem, the first step, is that, in fact, and it's something quite interesting, that the Clapoti algorithm solves directly the case where if G equals 1. So really, you can think of the Clapoti algorithm, the one who smooths an ideal, as a way to compute a generator of an ideal, assuming that you can invert the prime L. So it's funny because it's not something that we use to, it's not like that we usually present Clapoti algorithm, but it's really the same thing. And once we have this powerful tool unlocked, given by the Clapoti algorithm, we can really conclude by a simple all-linear algebra. So I won't go into the detail here because it would be a little bit too messy, I think, but this is all we need for the first step. And so the second step, it may be a little bit more tricky, because we now have to principalize our ideal precisely at L, but the main constraint is that we have to be very careful about the operation we are going to apply to our ideal. We cannot do whatever we want because we don't want to destroy the work we did for every other prime Q. This means that, in fact, you are going to compute a very specific element in this very specific set of matrices, which are the elements that are invertible, assuming that you can invert the prime L. And since the fact that alpha 2 will belong to such a space will ensure that we will not destroy what we did before. And so that will allow us to conclude afterwards. Maybe here the ingredients are a little bit different, because to find such alpha 2, we really crucially relies on the fact that there is enough invertible elements in the matrix space MGO. And afterward, we can conclude by linear algebra over the L-adix integers, but very maybe not so naive linear algebra for this step. So just I wanted to spend just a few seconds about the first ingredient, the fact that it's easy to find invertible element in the matrix space. For example, we can take permutation matrices, and it gives us a lot of examples. I insist on that because at first, Aurel had an algorithm that would work for any central simple algebra over some number field, but it fails to be polynomial at some point because he had to find some inverse in some algebra. But here, in our case, working with matrices, this step is in fact easy. So here we can gain the sub-exponential complexity that was before. So now we will have a polynomial time algorithm. So I conclude this algorithm by saying that now we have I and the principal ideal generated by alpha 1 product alpha 2, which are equal locally everywhere. Thus, by the local global principle, we in fact have the same ideal on both sides. So, few remarks before moving on to the next section. First, we have to assume the general Riemann hypothesis to say that our algorithm runs in polynomial time, since we call Clapoti. Now, we also implicitly reduce to the case where the ring O has a specific element Q, whose reduced norm is precisely the small prime L. So this is something very unusual when you look at maximal quaternionic order. It's really an extremal property. But in fact, we show that we can simply reduce to the case, and that helps us a lot. Okay, and if you want to, so this is the algorithm that we implemented with Damien and Aurel. And if you want to play a little bit with the implementation, so it's you can find it at this link. I tried to comment it a lot, so I hope it will not be too messy to read, but yeah, if you want to have fun, you can play with it. Okay, so
Julien,
yes,
we have a question in the chat. I think that has answered, but Haroon asked, does Clapoti have some heuristics rather than GRH?
Oh yeah. At first, Clapoti has a lot of heuristic, but yes, okay. Damien said it. Yeah, okay. Veselowski also proved another version of the Clapoti algorithm that work without any other heuristic than the general Riemann hypothesis. Yeah. Okay. So it's proved under the GRH. So if you have any other question, you can ask before I move on. No? Okay, so maybe later. So now I really focused on the object. I really focused on finding a basis of my module. But what happened to the morphisms between my objects? And that the main topic of this section 3. We are going to introduce our new version of the Clapoti algorithm, and I'm going to also describe some application of it. So on the geometric side, we have the isogenies. So quick recall, there are surjective morphisms with finite kernel and between abelian varieties of the same dimension. Also, we can give the definition of an isogeny being an isogeny that respects the polarization that we put on the variety. So if we translate it to the module world, reversing the arrow, since it's an anti-equivalence of category, we end up with what we called module isogenies, being this time injective morphisms with finite co-kernel, meaning that MA divided by the image of psi is finite. And in a similar way, we can define what are the module isogenies that respect the Hermitian forms that we put on module, and we call them N similitude. So once again, this is a kind of abstract way to find those module isogenies, and I'm going to give some example. So in dimension 1, if we fix some element x of an Hermitian module, MHM, then we can look at the action of O on those elements. So this is precisely the map that is here, where lambda is an element of the ring O, and we act on the left of X. So this, in fact, will induce an isomorphism between the base Hermitian module, the easiest one, and this other principal Hermitian module. In particular, this means that every such principal Hermitian module corresponds to the same isomorphism class of principally polarized abelian surface, being E with its principal polarization. Another example that we used a lot in our paper is given once again by ideals. So if we look at an ideal of O, then the inclusion of I inside O gives us a similitude with polarized degree, the reduced norm of I. So here you notice that I put the good Hermitian form on I, so that I'm working with unimodular Hermitian modules. So once again, it's really close to what happened when we are working with ideal through the Deuring correspondence. An ideal induces an isogeny whose degree is related to this reduced norm. Okay, so the general idea of this second example is that since on the geometric side we are working with surjective morphisms, in the module side we are working with injective maps. This means that to compute isogenies between polarized abelian variety, we can in fact construct specific submodules of the module we are working with. Okay, and this will be one of the main properties that we're going to use to present the new HD Clapoti algorithm. So before going to our generalization, I just wanted to say a few things about the Clapoti algorithm itself. So here we are more in the oriented setting, where we have an elliptic curve E, which is oriented by a quadratic imaginary order R, and I want to compute the action of an ideal of R on my elliptic curve E. So the tools that used Damien and Aurel in their paper was to first compute two ideal of coprime norm, which are equivalent to A, and then use a Kenny diagram to recover an isogenies in higher dimension whose codomain will have the elliptic curve that we want. So you can really see here that we have this notion in some sense of having double pass. You can think, if you if you see this, if you see those ideas as things that link two elliptic curves, we're really asking to have some double pass between two curves. And so what we want for Isogeny Clapoti is exactly the same thing. We want that to be able that given the Hermitian module MHM, we want to compute the action of this Hermitian module on the fixed base curve E. End up and recover representation of A together with its polarization. So here, when I compute a new representation of A, it can be given, for example, by theta coordinates. We just want a representation that allows us to perform some usual algorithms that we want to do with abelian varieties. And so the idea of our Isogeny Clapoti algorithm is really the same as the one in one dimension, because we are going to construct double paths between A and e to the g that will allow us to, as explained in the paper of Damien about the module action, to recover the abelian variety A. So it's really the same idea. We're going to try to construct those double paths, which translates in the module world to compute two coprime similitude, two similitude of coprime degree. And so to do that, as I said, we are going to look at very specific submodules of M that will give rise to such similitudes, in fact. And so we try to construct these good modules, and in doing so, we need, in fact, some very technical tools that is called the Poincaré decomposition. It is the exact analog of what happened in the geometric world of abelian varieties, which really is a crucial tool that we develop in our paper, since we use it for generalizing the Isogeny Clapoti algorithm, but we also use it to improve the output complexity of KLPT2 algorithm. So it's rather a technical lemma, so I'm not going to present it today, but it's really something important for us. Okay. And so now that we have our double pass, I just wanted to highlight a consequence that I find beautiful, is that now, given this module representation, so given M and an Hermitian form representing some polarized abelian variety, we can compute an isomorphism between A and e to the g, so the maximal abelian variety of dimension g. So the next slide is the technical slide of my presentation. We are going to draw some picture to try to explain how we do that. So the first step is to compute our coprime double pass that we have through the Isogeny Clapoti. Then, with our solution to the principal idea problem, we can compute an isomorphism between M and O to the G. Okay. And so what we want to recover on the geometrical side of abelian variety is precisely this map, okay? This isomorphism. So to translate it back, we cannot translate it back like this. We have to construct double pass. And so one natural double pass that arises when looking at this diagram is just given by the composition. So the red map, the red arrows, are the composition of the blue one together with psi on both sides, because we have two paths of coprime degrees. So now we can translate the blue and the red arrow back in the world of abelian variety, and we end up with isogenies looking like this. And we're trying to we want to try to recover this phi, which is the map that corresponds to this psi. And so we want to try to evaluate phi on a point. But now we have two different ways to divide phi into other isogenies. So suppose that we want to evaluate phi on a point P, whose order is coprime to the D1 being the degrees that we have in the upper side of my diagram. If it's not, we can just do the same argument, but on the lower side of my diagram. Okay, and so to compute phi of P, I can just do this pass where, thanks to phi1 prime, I can go to e to the g, and then computing the dual of the I can recover a multiple of the points that interest me on A. And then, since I assume that I have that P have an order that is co-prime to D1, I can divide by D1 and recover the point that I wanted. Okay, so this was the technical side. I hope that I have been a little bit clear, but it's really that idea that double pass allows us to evaluate on any point. So it's going to be an idea that I'm going to use again in the following few slides. So, as I said, this module representation and these tools that we have will allow us to now switch between the different representations that I have. For this tool, I will mainly focus on the endomorphism ring representation as we have in one-dimensional theory. So just I'm going to fix some notation and some terminology when I mean that we want to compute a complete representation of the endomorphism ring of A and of some polarized data given by the Rosatian evolution. I mean that we want to compute first a set of a generator inside the ring R together with the Rosatian evolution R, little r. Moreover, we also want to know how we can multiply elements of such abstract ring R. And finally, we want to have access to algorithms that allows us to evaluate elements of R that is isomorphic to the endomorphism ring of A on any point of A. Okay, so we're really asking those three things. First, we can notice that we have a natural choice for R. The fact is, since our maximal abelian varieties are, every one of them are isomorphic to a power of E, then we can just take R to be this matrix ring, which is naturally isomorphic to the endomorphism ring of E to the G. Okay, so the ring that's going to interest me is this one. The whole problem is now to find the good involution to put on R and to find an algorithm to evaluate those matrices on point of A, which is not a product a priori. And so to do so, I'm going to suppose that we have access to the module representation of the abelian variety A, and that we fix an action of the matrices over E to the G. Okay, it's really, so you decided to ordinate the coordinates of an element of E to the G, and you choose maybe in the more natural way, or a matrix applied to such a vector of coordinates. So it's really something very natural, but we need to fix some action at first. And so the tools that we developed until now allows us for first compute and recover the polarized abelian variety A lambda A associated with M, and then compute an isomorphism and its inverse between A and E to the G. Okay, so if I do that, I can draw such a diagram where we're going to try to evaluate a matrix alpha on the point of A. We are trying to compute this map. And so we see that it suffices to go from A to E to the G, use the natural action that we have of matrices over this abelian variety, and then by psi we recover an element at the end of A. So we can really compute this path right here, and that gives us an action of alpha over element of A. Now to recover the Rosatian evolution, we can in fact look once again at the pullback of the Hermitian form we had on M. We look at this Graham matrix, we call it S, and we have now a conjugation map in the matrix field that in fact gives us the good involution. Before moving on, I just wanted to notice that this gives me a well-defined couple, R and RS, in the sense that if we change the isomorphism we took, we end up with more or less the same couple. And in fact, in our paper with Damien and Aurel, we made something a little bit more general, because if I took a little bit of a high-level perspective here, what we did is that in order to compute the action of an element of a morphism here, thanks to the double pass that were hidden in my isomorphisms, but thanks to double pass, I can reduce this to the computation of another here morphism. So if I know how to evaluate morphism between A2 and B2, thanks to double pass, I can recover how to act by morphisms on N1 to B1. So this is really the general setting. As I said earlier, having double pass will allow us to evaluate things on every point we need. So just before concluding, I wanted to make a slide because at some point at the first site, we missed something in our paper. The fact is, what if we're going to try to do the converse? What if you give me abstract ring R together with an evolution? Can I recover the Hermitian module corresponding? The fact is, this question is not well posed because, as told us Montesino, those two modules, which are not isomorphic, led to the same couple, the same isomorphism class of couple. So this is, if we look at it from abelian variety side, in fact, it corresponds to the fact that A and the Frobenius conjugate of A have the same type of endomorphism class of endomorphism rings. And it comes from the fact that when we look at the automorphism of this matrix space, we have one class that doesn't behave like the other, which is given by conjugating by the Frobenius. Okay, but fortunately, Montesino in his paper also provide a solution to this problem that here I reformulate in terms of modules. The thing is to be able to going back to the module world from a complete representation of the endomorphism ring. We need to remember how M act on some special space, but we really have to take something more into account if you want to recover the precise Hermitian module. So that's all I wanted to talk about. I'm going to conclude now. So I presented several algorithms, one that can solve the principal ideal problem, one that can allow us to compute explicitly the module action. And I just wanted to talk about some perspective for future work. First, we can look at optimized implementation. Of course, I did not try to provide the best algorithm to, for example, compute generators of a given ideal. And I wanted to mention that the COSIC team in Leuven managed to also find another solution to the principal ideal problem that doesn't call the Clapoti algorithm. So we expect that their solution might be faster. Also, something that can be very interesting is to have a closer look to the crypto system mic that Damien introduced in his paper about module correspondence. Because, for example, I'm not sure at all how far are we from having a practical implementation of this crypto system. So really, I don't know. And finally, maybe a more technical remark is that in some of tools, the very fundamental lemmas that we have, we use some assumption at a lot of points where we need the Hermitian module we are working with to be unimodular. This means that we are working with principally polarized abelian varieties. And maybe if we manage to get rid of this assumption, we can have a simpler and more general algorithm that would apply. So if you want to learn more about this work, I hope that you're gonna to have a look at the ePrint that is online now. And okay, so that's all for me. I thank you everyone for your attention. If you have any question, please ask. I'm here for it.
Thank you very much for a great presentation, Julien. Yeah, as Julien said, feel free to type questions in the chat or just unmute and ask them out loud. So maybe I can go first. I just very quick, maybe like a simple question, but on the previous slide. Yeah, so this one, sorry. Oh no, the next one. The one with the yes.
Yes, okay.
The ambiguity, exactly. So this even happens in dimension one, right? Like
Yeah.
and I'm just wondering like how concretely do you remember?
Okay. Okay, so it's a little bit technical. So Montesino, in his paper, he showed that. So he's working with IKO matrices. So in a framework that is just a little bit different from us, but he shows that by having some infinitesimal information, we can remember if a couple gives us one module or the other. And so in terms of Hermitian module, so you see that the problem is lying at when we look at the conjugation by J. Okay, and J gives rise, in fact, to an ideal in the matrix space over O, which is the only two-sided ideal of norm P. This one. Okay, and in fact, working with global differential of the abelian variety amounts to look not at a FP algebra structure, but at a FP squared algebra structure on this particular ring. So, in fact, what we remember in some way is, are we in the FP squared structure, are we trying to conjugate the element or not? I'm not sure if I'm clear, but it's very hard to tell about it without writing the details. But you see that the information is kept inside this two-sided ideal, which is the only one of norm P. And so if we look at the endomorphism ring of this quotient, we can try to take the specific information that we need. And in fact, what we need, as shown in Montesino, is that we need to be able to understand how behaves the global differential on our variety. And so that's what we call a refined representation when we have such a couple, so with generators, a way to multiply them and a way to evaluate them, plus another information that we need to distinguish between the two. Maybe a very easier way to say that is that we just need to remember if I is sent to I or minus I. It's really the only thing that we need.
I think I might have to think a bit more about it too, but I think I get the idea.
Okay.
It's cool. Yeah, are there any more questions?
I
had actually wait, let me turn on the camera. So I had a question actually very far at the beginning when you had this theorem about maximal abelian varieties having this isomorphism to a product of curves. So I thought this was like the definition of super special. And then I was wondering if all maximal are super special or super singular or...
So yeah, the theorem said that every maximal abelian variety is super special.
But you would imagine that you also have like super singular, non-super special maximal varieties or not?
Can you repeat? You can think of what?
You would imagine that you would also have like super singular but not super special maximal varieties, or it doesn't happen, or this was what confused me a bit.
Okay, so when you mean super singular abelian varieties, you mean?
Isogenous to a product of curves.
Okay, so just isogenous. Okay.
Yeah.
Okay. So yeah, it's a theorem, so it's hard to explain it in detail. But yeah, the theorem said that if you look on so fp squared, okay, so there is other theorem if you look at the closure of fp. But if you look at varieties that are isogenous to this product, then by the Tate theorem, they have the same cardinality. So in particular, they are maximal. And then the theorem tells you that more than being just isogenous, they are in fact isomorphic.
So yeah, but the other way around, right? Now you start with a maximal one.
So if I may, I think it's not really Schoda's theorem here, because like if you have a superspecial abelian variety, it's isomorphic to e to the g over fp bar.
Yeah.
But there is a stronger theorem that says that if you have a maximal abelian variety over fp square, then it is isomorphic over fp square to e to the g. And it's a version of fp square, not of fp bar. And I think it's not from Schoda, it's actually later from the paper by Tate and Aurel. I'm not sure it was known in Schoda's case.
Okay.
So it's really like maximal is nice. It's allowed to everything we know about superspecial abelian variety over fp bar. We can put it back to fp square by restricting to maximal thing. And we really have a connection between fp square, maximal, and fp bar superspecial.
Yeah. Okay. And so we don't have to, and working with maximal abelian varieties, the cool thing is that we don't have to deal with the weird twists that we can have. So we can speak in terms of cardinality, and already works nice.
Cool, nice, thanks.
Oh yeah, so there is a question about the link with KLPT in the G1 case. Yeah, so when I was saying that KLPT allows us IMG to principalize precisely when we can invert L. So this one, I think. So when you look at KLPT, what it gives us is an equivalent ideal of I, whose norm is power of L, say. So it means that if we multiply I by the element given by the KLPT algorithm, we end up with an ideal whose reduced norm will be precisely L to the n, say. And when an ideal is of reduced norm L to the n, it means that you can write it with two terms. So I cannot write anything, I'm sorry, but it means that you can write your ideal G in one term generated by some element over O plus another term generated by the reduced norm precisely of the ideal you have. And so if you assume that you can invert the element, the prime number L, where you trying to that you want to inverse, and where you smoothen your ideal, then the second term, the plus reduced norm of I O, disappear since you have the right to invert L. Okay, and so at the end step, you end up with assuming that you can invert L, have your element, your new equivalent ideal G, which is precisely generated by a single element, sorry. So it's my bad, I have nothing to write, but no, I have nothing. But it can really be seen as a direct consequence. Yeah, it's the same idea, yeah, as what you write. Yeah, if you are allowed to invert L, in fact, the second term disappears. Yeah, the O L plus L to the power. Yeah, thank you very much. My pleasure. Thank you for your question. And so I think in my implementation, I think I use your implementation of Clapoti, Jonathan, that you did for Deuring correspondence for people.
Aha.
And you have a GitHub repository for it. And I stole of all your work for having a Clapoti algorithm. So thank you.
Yes. Well, it was also written by not only by me, but it's indeed from one of the first papers I ever worked on. So it's very nice. But then yeah, I will apologize for any bugs in that you encounter. So yeah, sorry. Maybe I think I must have missed this, but so in step one, you principalize almost everywhere, so except from at L.
Yeah.
But what? So this is very basic. But what is L? Like which prime do you? Can you choose any L or?
The difficult part is to decide which L to take.
Yeah. Okay.
But there is a subtlety that, in fact, when I was presenting this algorithm, I assume that in O there is this special element of reduced norm L. So in fact, the precise statement is that what I presented you work if you prime L ramifies. So you want or split more. You want to have an element whose reduced norm will give you L. And so it's not possible for many order, but for example, if you look at the O0 given by the endomorphism ring of the base curve, then it's easy to find element of that realizes prime norm. It suffices to take, for example, 5. It works, 1 plus 2 squared, so and you're good.
Okay, I see. Oh, very cool. Thanks. Okay, then are there any more questions? Did you not have one, Maria? Or?
Yeah, but maybe I can ask it after we turn off.
In that case, let's thank Julien again.
Okay, thank you all. Thank you very much.
Great presentation, thank you. And then next week, Maria, do you want to advertise a bit in 2 weeks?
Yeah, so we'll be back again in 2 weeks with a presentation by Haroon Kier from Lyon. And he'll be talking about the expansion properties of the super special isogeny graph. So yeah, we look forward to seeing you all then.